Detection and quantification of radioactivity lies at the core of imaging and therapy techniques. Different instruments can be used to measure or detect radioactivity. For example, to administer the correct dose of radioactivity to the patient, the radiopharmaceutical is placed inside a dose calibrator to measure the amount of activity present. In the dose calibrator, radioactivity of the sample is measured using a gas-filled ionization chamber. Inside the chamber, the radiation ionizes the gases, which then generate an electrical signal. The low applied voltage of the ionization chamber allows accurate measurements of the number of ions. The electrical signal is directly correlated to the amount of radiation. Once the electric signal is measured, the gas is neutralized and it is ready to interact with more radiation. The dose calibrator is a convenient way to measure the activity of different radioisotopes. A disadvantage of this detector is that it gives a cumulative activity reading of all the radioisotopes present in the sample. Hence, the amount of activity of a particular radioisotope in a mixture cannot be determined using this detector. Furthermore, the measured activity depends on the geometry of the radioactive container and could vary substantially from the theoretical activity, especially for electron emitters. In the nuclear medicine department, other instruments, such as the Geiger counter, are used for monitoring activity levels in areas. Radiochemists use it to frequently survey their gloves while handling radioactive samples to avoid contamination through their gloves. It is kept in the general vicinity of their workplace to monitor activity levels in unshielded regions. Stationary area radioactivity monitors are present in common areas to warn of high levels of activity. Monitors are also placed outside of the radioactive facility to scan personnel leaving the facility. All personnel working in nuclear medicine are required to wear a dosimeter. It provides a cumulative estimate of absorbed radiation over a certain period of time. The body dosimeter is worn near the chest and the ring dosimeter under the gloves of the radiochemist. The crystalline material inside the dosimeter traps the electrons during irradiation, which at a later time can be measured using light stimuli. The dosimeters are analyzed on a monthly to quarterly basis. This allows one to estimate the effective dose absorbed by the body. The estimated effective dose is compared to the annual dose limits to evaluate regulatory compliance and trends in exposure. In case of higher than normal exposure levels, radiation safety officials discuss working protocol and handling of the radioactive material with the involved personnel to achieve lower exposure. Imaging of patients injected with radiotracers is performed using single photon emission computed tomography or positron emission tomography. In particular, SPECT imaging is used for gamma emitters, whereas PET imaging is used for positron emitters. In a SPECT imaging device, the radiation emitted by the radiopharmaceutical passes through the body and is detected by a gamma camera. There can be 2 or 3 cameras in a SPECT device. The camera contains a large planar crystal, such as a thallium-doped sodium iodide crystal, which can detect gamma rays in the energy range from 60 to 360 kiloelectron volts. The gamma rays are collimated before incidence on the crystal. The light generated by the crystal is enhanced by photomultiplier tubes. The pulse height analyzer sorts out the signal based on the signal amplitude, differentiating gamma rays of different energy. Finally, the signal is digitized and recorded by the computer. During the measurement, the gamma camera rotates around the patient. Thus, acquisition from multiple angles is obtained, allowing a computer to tomographically reconstruct it to generate 3D images. In the PET imaging system, the radioactivity signal is detected by different crystals cylindrically arranged around the subject. The crystals detect two gamma rays of 511 kV ejected 180 degrees apart from the annihilation of a positron. The detection of these two gamma photons occurs within the coincidence acceptance window of 5 to 10 nanoseconds. Gamma photons detected outside of this window are considered as noise and rejected by algorithms. Using this information, the location of the radioisotope can be determined. Crystals used for detection can vary in geometry and the type of material. They can be curved or block-shaped. They can be made of bismuth germanium oxide, gadolinium silicon oxide, and sodium iodide. The choice of material is governed by sensitivity, counting speed, energy resolution, and cost. Depending on the goals of the imaging experiment, the acquisition mode of SPECT and PET imaging can be changed. The images are acquired in static mode when a snapshot view of the biodistribution of the radioisotopes in the subject is recorded. Images can be acquired at different time points after injection. Depending on the radiopharmaceutical, the time needed to accumulate at the region of interest can vary. For example, in the case of fluorine-18 falciparum, the peak accumulation at the striatum is at approximately 60 minutes, whereas for that of carbon-11 raclopride occurs at around 10 minutes. These both are dopamine D2 binding ligands from same structural family, but with different pharmacokinetics. In the dynamic mode, consecutive images are acquired over a period of time showing the changing distribution of the radiopharmaceutical in the organ of interest. A whole body acquisition can be performed to visualize more widespread distribution or accumulation in unknown locations. The rhythmic motion of some organs of the body, such as the lungs and heart, could lead to artifacts or blurring in the images acquired. To avoid this problem, the images acquired during the same phase of the rhythmic motion are aggregated. Such imaging is called gated imaging and allows the visualization of diseases despite of the movement. In nuclear medicine, dedicated devices are used to ensure that the proper radioactive dose is administered to the patient, as well as to ensure that radiochemists and doctors can work safely in the lab, avoiding excessive absorbed doses. Transformation of the detected emissions from radiopharmaceuticals into images allows us to detect various diseases and investigate human health.